Good morning. Today we'll discuss about three-phase induction motor. In the last lecture, we have discussed about transformers. We have seen the operating principle of a transformer, and we have also seen what are the important components of a transformer, and we have derived an expression for the EMF equation. And the EMF equation was E is equal to And the EMF equation was E is equal to 4.44 F phi N, where F is the frequency, phi is the flux, maximum flux which is developed, and N is the number of turns. So this was the expression for the EMF which is developed in the transformer. And we have seen that there are two types of transformers, namely the step-up transformer and step-down transformer. And we have also seen that the transformation ratio is defined as N2 by N1, which is also equal to E2 by E1. And ignoring losses, it is also equal to I1 by I2. So if the number of turns is greater on the secondary side, you will get a boosted voltage. If the number of turns is less, then you will get a reduced voltage. And if both the turns are equal, then there won't be any change in voltage level, and you call it as an isolation transformer. We have seen these things in the last video lectures, and we have done some numerical problems along with discussing some applications of transformers. In today's class, we will see about one more electrical machine which you will be using in your electronics engineering. That is a three-phase induction motor. So today's class, we will see what actually is a three-phase induction motor, what are the important components, and how it operates, along with where it is used. So I'll start with why induction motor and what is its working principle, and then we will move on to components and we will see what are the major types of induction motors, and then we will see the applications, and if possible we'll try to solve simple problems. Okay, let me start with the introduction. At our home we will be getting AC supply, isn't it? And it is single phase AC supply. But if you go for the industries, we will be having three-phase AC supply. And one more important thing, we human beings, we want mechanical energy 24/7 at our homes or for our daily needs. You take an example, the fan which is above me, I don't need a fan 24/7 all the time, or otherwise I don't need a cooler, or otherwise I don't need a fan, or otherwise I don't need an AC or any other things. So what are the mechanical energy which I want? It is basically coming from a motor. A motor is a device which converts electrical energy to mechanical energy. And this mechanical energy is being used by me. So any device which converts this electrical energy to mechanical energy, we call it as a motor. There are so many types of motors in use, but the primarily used one is an induction motor. Mostly 80% of the motors which are being used now, these are all induction motors. And these motors, they do work on AC supply. And when we talk about AC supply, we do have two types which we have discussed in the last unit. One is three-phase, the other one is a single phase. For our domestic applications, we do use single-phase motors. Whereas for industry needs, where large amount of power will be dealt, we will be using three-phase induction motors. Okay, so three-phase induction motors is our today's topic. So it is used widely in industry applications. We don't see them often in our domestic applications, but when you go for the industry, you will be using these induction motors for a wide variety of applications. And this is also same like your transformer. It works on the principle of electromagnetic induction. So it works on the principle of electromagnetic induction. And before I go for this concept of electromagnetic induction, I'll just give a small glimpse of rotating magnetic fields. Don't bother, I'll just only give a small glimpse. Try to understand. See, when I provide a single phase AC supply, say let us suppose this is now this is two poles have been created here, and I'm allowing a current to pass through it. So when a current is passing through it, then automatically we will be getting a magnetic field, and these will act as north and south poles, right? So the magnetic field which is developed between these two, it will be, if I provide AC supply here, then the developed magnetic field also will be varying in with respect to time. But it won't be varying with respect to space. It is fixed, it is between only these two lines. And the fact is that its magnitude will be changing. Sometimes it will be stronger, sometimes it will be weaker. Okay, so now this is single phase AC magnetic fields. Now, if I provide a three phase supply here, I'll show you in one more slide. So when I use this, I'm not a good artist, so this is what I talked with you as a right. This is only one magnetic field which is not varying with respect to space. I'll write it here. This is phi, not varying with respect to space. Not varying with respect to space, but varies only with respect to time. But varies with respect to time. Okay. Now, a three-phase supply. Now, let us suppose if I take now this is one. Okay, this is R1 and R2. These two are connected, and this is, take it as Y1, and this is Y2, and this is B1, and this is B2. Now I'll assume that these are being fed by a three-phase supply, R by pi. This is R, it's this fields, and whereas this is Y fields, and this is B fields. Now all these three fields, they are varying with respect to time. The magnitude is varying with respect to time. Now if you apply all the three fields together, then there will be a resultant magnetic field, right? Now the resultant magnetic field, see, the R phase, it will be like this. Y phase a little bit later at 120 degrees like this. And B phase, it will be still later, it will be like this. Okay. So all the three phases are separated by 120 degrees. Now there will be a resultant magnetic flux, right? And that resultant magnetic flux, whatever is being produced here, it basically, it will be constant in magnitude, but it will be varying with respect to space, not with respect to time, which means that there will be a magnetic field, and that magnetic field will be moving in this fashion. It will be constant. It will be 1.5 times of individual phase, and it will be moving in this fashion. So at any instant, if you see, it is physically rotating with respect to time. This is the magic of three-phase AC supply. A single-phase AC supply, you will feel only a stationary magnetic field, which is varying with respect to time. But if you use a three-phase AC supply, you will feel a magnetic field which is rotating with respect to space, but is having a constant magnitude of 1.5. That is a magic of three-phase AC supply. And you call this magnetic field as rotating magnetic fields. And you call this one as rotating magnetic fields. Now, what are the advantages of this rotating magnetic fields? A three-phase induction motor utilizes this concept of rotating magnetic fields. Now, I will show you how a rotating magnetic field is advantageous for me. We will move on to the operating principle now. Okay. Now, instead of reading all these things, so let me make a quick thing. See, a three-phase induction motor, it operates with three-phase AC supply. It is a singly excited system. Okay. So, but before going for this one, let me take one more empty slide and let me explain to you again what actually happens in a three-phase induction motor. So what actually happens in a three-phase induction motor? Okay, I'm not a good artist, but I'm trying. Once again, I'm repeating it. Yeah. Okay. Now, see, this magnetic field which is being developed by this three-phase, it is varying with respect to time. Now, I'll use a conductor here. Okay, now this is your magnetic field which is developed and it is rotating with some speed, and that speed is called as synchronous speed. We call it as synchronous speed. What is this one? This is the speed of the rotating magnetic field which is developed by your three-phase supply. And its formula is given by 120 F by P. Try to remember, it is 120 F by P, where F is the frequency and P is the number of poles. It is number of poles and it is frequency. This is represented by Ns. So now your field is automatically rotating with respect to space. Now if I keep a conductor here, what will happen now? This conductor, since see it is just a normal conductor which is stationary. So what happens when you do have the field which is moving around you? So automatically it is cutting the magnetic flux, right? So your conductor is now in a magnetic field which is varying with respect to space. What will happen? There is a cutting of magnetic lines of force by the conductor, right? So this automatically what happens? EMF is induced in the conductor. EMF is induced in the conductor. Isn't it? Now you do have a 3 EMF which is induced in the conductor. Isn't it? Now these terminals, whatever the terminals which you do have, here a small EMF will be developed here. Okay. Now if you provide a short circuit across conductor, what will you get? You will try to get the currents. Current passes through conductor. When the current passes through a conductor, what will happen immediately? Field will be developed. Field gets developed. See, it means that there is a local field which is being developed here. This is your external fields, and there is a small local field which is being developed here. Now, because of this, what happens? Now, there is an interaction of two fields now, right? Interaction of two fields. What will happen with this one? Torque is developed. Right. What do you mean by torque? It is nothing but a mechanical movement. So which means that your conductor is now, conductor starts to move and tries to catch Ns. Got it. Now, here, when your rotor or your conductor, when it tries to catch up the rotating magnetic fields, let us suppose your conductor, I'll write it here. Let's rotor speed is nr, and your synchronous machine is having a synchronous speed of, sorry, your synchronous speed is ns, right? So when nr is equal to ns, what will happen? When nr is equal to ns, there is no relative motion. Both are moving at the same speed, right? When both are moving at the same speed, there won't be any relative motion, right? So which means that no EMF is cut, which means it ceases to be an induction motor. No EMF is generated, no current, so no torque, nothing. So immediately it will fall back. Once again, if both are moving at the same speed, will there be any flux cutting? No flux will be cut. No flux cutting means no EMF, no current, no torque. So your NR can never be equal to NS. This is what happens. Okay, so your rotor always will be rotating at a speed which is less than your synchronous speed. But if you want forcefully, you can increase it to a value larger than ns, but that is a different case. But normally an induction motor never runs at a synchronous speed. That is why it is called as an asynchronous motor, because it never runs at a synchronous speed. Okay, and the difference between a ns minus nr, it is called as a slip speed. We call this one as slip speed. Okay, now, so this is my principle. A three-phase induction motor operates with three-phase AC supply. It is a singly excited system. What you are doing, you are just providing three-phase AC supply. It is developing rotating magnetic field, and your conductor EMF is induced. Short circuiting it, it provides current, and then magnetic field. Interaction of two magnetic fields, torque is developed. So what you are doing, just you are providing three-phase AC supply and ensuring that your rotor is short circuited. Okay, so it consists of a stationary part, which is a stator, where your three-phase field will be set up, and a rotor, rotating part. Your conductors will be set up in the rotor, okay, such that they must be able to move, right? So the stator is provided with three-phase AC supply, and it develops a rotating magnetic field which will be varying in space, and only a three-phase AC supply can develop it. A single-phase AC supply cannot provide that magic. Now, when the stationary conductors on the rotor, when they cut this magnetic field, what will happen? EMF is induced. This is the principle of transformer, right? So a three-phase induction motor, under normal conditions, under stationary conditions, it is just like a transformer. What additionally you are doing? The rotor is being short circuited, either directly or through some external resistance. Current flows. Automatically what happens? There is a local magnetic field. Now current carrying conductors, under the impact of magnetic fields, they will develop a torque, which leads to the motion of rotor. If you are not able to provide a motion to the rotor, if it is fixed, then it will just act as a transformer. Now you are providing it, you are giving it an opportunity to rotate, so it is moving. When it is moving means kinetic energy is being produced, which is a form of mechanical energy. What is the input which you have given? You have provided three-phase AC supply, which means you are providing electrical energy. What you are getting? It is moving, right? Mechanical energy you are getting. So your fan also, your industries here, etc., they work with induction motors. This is how, providing electrical energy and getting mechanical energy. With that movement, you may move something. Here fan, air is moving, I am getting air. Let us suppose you have a conveyor belt. So if you fix it, conveyor belt will be moving, like that. So mechanical energy is being developed. I hope you have understood this principle of operation, right? See, the speed at which it rotates, the speed at which rotating magnetic field moves is given by synchronous speeds. Okay, and the rotor starting from west, it tries to achieve these speeds. What happens if the rotor speed is equal to synchronous speed? The relative speed becomes 0 and the motor stops working. And as a result, EMF induced will be 0 and there will be 0 relative movements. Okay, so that's fine. It is assumed that rotor does not attain synchronous speeds. It will be always falling behind the synchronous speed. And the speed at which it rotates is called as rotor speed. I'll name it as omega or omega r. Okay, now try to remember, this induction motor never runs at synchronous speed, and hence it is called as asynchronous motor. Okay, and the difference between this synchronous speed and the rotor speed, you call it as, see, difference between synchronous speed and the speed of the rotor is called as slip speed, and the ratio of slip speed to synchronous speed is called as slip. Okay, I have written this formula. See, or how synchronous speed is determined: 120 f by p, where f is the frequency and p is the number of poles of your machine. And what is slip speed? Ns minus nr. Ns minus nr by ns is the slip, and if you want to have percentage, into 100. Okay, slip speed by synchronous speed into 100. Okay, with this I am closing this video, and we'll discuss the construction and the types in the next video. Okay, thank you.